Hello good day viewers. In this tutorial we are going to learn how to solve differential equations using Laplace transforms. But it is always very important to know how to take the Laplace transforms of different functions as well as inverse Laplace. It is also very important to know how to resolve compound fractions into partial fractions. In our introduction to Laplace transforms, we have seen how to take the Laplace transforms of different functions. The only new thing here is how to find the Laplace transform of some derivatives, which we are going to learn in this tutorial. We want to find the solution to y prime is equal to cosine x. We are given an initial condition when the value of x is equal to 0, y is equal to -1. What we need to do here is to take the Laplace transform of both sides. And let us do that. We have the Laplace transform of y prime. This is equal to the Laplace transform of cosine x. But how can we find the Laplace transform of y prime? We have no problem with the right hand side. We even have the table. I will show you that. All right, let me highlight the formulas for you and the simple way to master them. Suppose you want to find the Laplace transform of y prime prime prime, where the order is 3. This is equal to s to the power of 3, because the order is 3, multiplied by the Laplace transform of y. Then you subtract. The power of s will reduce by 1. We have s squared, multiplied by y of 0. You can see we introduce y, minus the power of s will reduce by 1. We have s. Then this time around we have y prime of 0. The order of our derivative is increasing while the power of s is reducing. Then lastly, you have to stop when s vanish. The power of s will reduce by 1, so we have s power 0 equal to 1. But this time around we have y prime prime of 0. If you look at this pattern, the power of s is reducing, but the order of derivative is increasing. What if you want to find the Laplace transform of y prime prime, which is double prime? This is equal to s squared because the order is 2, multiplied by the Laplace transform of y, minus the power of s will reduce. We have s, y of 0. This time around, s will vanish. In the third term, we have just y prime of 0. And if you want to take the Laplace transform of only y prime, this is equal to s because the order is 1, multiplied by the Laplace transform of y, then minus s will vanish. We have only y of 0. All right, so now you can see that the Laplace transform of y prime is equal to s multiplied by the Laplace transform of y minus y of 0, which we have to substitute here to the left. So let's continue solving our problem. To the left, we have s multiplied by the Laplace transform of y minus y of 0. This is what we have to the left. So what if we want to find the Laplace transform of cosine x? Remember, in our introduction to Laplace transform, we have learned that if you want to take the Laplace transform of cosine of bt, this is equal to s divided by s squared plus b squared, where b is the coefficient of t. But this is a function of t. We are dealing with a function of x. Therefore, we can replace t with x. So we have x instead of t, and the function remains the same. But let me show you this under a table. I don't want to be giving you everything of head. Can you see that? Whenever you take the Laplace transform of cosine bt, you end up with s divided by s squared plus b squared. All right, but here our b is equal to 1 from the right hand side. Can you see that we have only cosine x? Therefore, the Laplace transform of cosine 1x, let me call it 1x, will be equal to s divided by s squared plus 1 squared, because b is equal to 1. So this is what we need to substitute to the right hand side. Therefore, we say this is equal to s divided by s squared plus 1 squared, which is the same thing as 1. So now let us substitute our initial condition. You can see it here. Y of 0 is equal to -1. Instead of y of 0, we write -1. S multiplied by the Laplace transform of y minus -1. And to the right, we have s divided by s squared plus 1. The whole of this becomes 1 because minus minus is plus. So we have s multiplied by the Laplace transform of y plus 1. And this is equal to s divided by s squared plus 1. Now we are free to take this 1 to the right, and it is going to become negative. We have to the left s multiplied by the Laplace transform of y. And to the right, we have s divided by s squared plus 1, then minus 1. But this minus 1, we can rationalize it as 1 divided by 1. And if we like, we can multiply the top and the bottom by s squared plus 1 to have a common denominator. So this becomes s squared plus 1 divided by s squared plus 1. Now we are free to simplify the numerator. To the left, we have s multiplied by the Laplace transform of y. This is equal to s minus s squared minus 1, because this minus will affect every term here. Divide by the common denominator s squared plus 1. We need only Laplace transform of y to the left, so we can divide both sides by s. The Laplace transform of y will now be equal to s minus s squared minus 1 divided by s multiplied by s squared plus 1. Now you can see that the right hand side is just a compound fraction that we need to dissolve into a partial fraction. And this can be written as a divided by s, which is the first factor, plus bs plus c divided by the second factor. I'll explain that. Why we have a constant here to the top is because the denominator is a linear function. Therefore, the numerator will be a polynomial of 1 degree less than the denominator. And 1 degree less than linear is just a constant. Here we have to have linear to the top because the bottom is quadratic. 1 degree less than quadratic will be a linear polynomial. All right. So let us clear the fractions by multiplying each term by s multiplied by s squared plus 1. If you do that to the left, you have only the numerator s minus s squared minus 1. And to the right, take this multiplied by this, s will cancel s, leaving only a multiplied by s squared plus 1. Do the same thing here. Take this multiplied by this. S squared plus 1 will cancel s squared plus 1, leaving s multiplied by bs plus c. Now let us expand this parenthesis. S minus s squared minus 1, this is equal to, distribute a inside the first parenthesis, we have a s squared plus a. Do the same thing to the other one. S multiplied by bs is bs squared, then plus cs. All right, let us bring those with s squared together. S minus s squared minus 1, this is equal to, we have one here, we have the other one here. You can even factor out s squared, so we have a plus b multiplied by s squared. Then those with s, we have only cs, and the constant, we have a. Okay, we are going to solve this equation by relating the coefficients. The coefficient of s squared to the right is a plus b. And the coefficient of s squared to the left is -1. You can see it here. So this becomes -1. Take the other one. Coefficient of s to the right is c. And the coefficient of s to the left is 1. The constant a will be equal to the constant to the left, -1. Now you can take this value of a, which is -1, plug it back into the first equation to get the value of b. Okay, so we have -1 as the value of a plus b equals -1. Take this to the right, it becomes positive, and positive 1 plus -1 is 0, so b equals 0. Now we have the values of a -1, b 0, and c equal to 1. We are going to substitute them back into this partial fraction to obtain our required fraction. So let me copy that. Remember that this is the Laplace transform of y. And this becomes a is -1, so we have -1 divided by s, plus b is 0, so the whole of this becomes 0. We only have c to the top, and c is 1. You can see it here. So we have 1 divided by s squared plus 1. All right, now we are free to take the inverse Laplace transform of both sides. Because we are looking for y, if you take the inverse Laplace transform of this, the inverse Laplace will cancel the Laplace, leaving only y. So y is equal to, you can take the inverse Laplace transform of these terms independently, separately. So we factor out -1. We take the inverse Laplace transform of 1 divided by s plus the inverse Laplace transform of 1 divided by s squared plus 1. All right. So now let us go through our table to find the inverse Laplace transform of these two functions. The first one is 1 divided by s. Can you see that? If you take the Laplace transform of 1, you're going to get 1 divided by s. Therefore, taking the inverse Laplace transform of 1 over s will give you back your 1. Therefore, what we have there is nothing but 1. This is equal to -1 multiplied by 1 plus. Now let us find 1 divided by s squared plus 1. If you take the Laplace transform of sine bt, you're going to get b divided by s squared plus b squared. Therefore, if you take the inverse Laplace transform of this, you shall get this back. And now we are going to apply that here. Let me even write it here. The Laplace transform of sine of bt is equal to 1 divided by s squared plus b squared. The same thing if you have a function of x, Laplace transform of sine of bx will give us 1 divided by s squared plus b squared. What if b is equal to 1? We have Laplace transform of sine x will be equal to 1 divided by s squared plus 1 squared, which is 1. Can you relate? This is exactly equal to this. Therefore, if you take the inverse Laplace transform of both sides, this will give you back sine x. The whole of this is equal to sine x. Therefore, we write sine of x here. -1 times 1 is -1. So this finally equals sine x minus 1. Therefore, y, which is a function of x, is equal to sine x minus 1. Wow. So now let us check by integrating both sides to see whether we're going to have the same function. Remember, what we are having initially is y prime equal to cosine x. If you integrate this with respect to x, you're going to get y. If you integrate this with respect to x, you're going to get sine x plus constant of integration. But remember, the initial condition says y of 0 is equal to -1. Can you see that here? So we are going to substitute the value of x equal to 0 and y equal to -1. This is -1 sine 0 equal to c. -1 is equal to 0 plus c, therefore c is equal to -1. Sine of 0, remember, is 0. Therefore, our solution becomes, you just need to substitute the value of c in this equation. We have y equal to sine x minus 1, which is exactly equal to what we have obtained here after using Laplace transform. And this is all I have for you today. Thank you for watching. Do share to your learning colleagues and don't forget to subscribe to my YouTube channel for more exciting videos. Bye bye.